Welcome. I'm delighted that you could join me as I present to you my project design proposal. My name is Patrick Ngala and this is a 3-pole Chebyshev bandpass filter design. It has no single application, but it is applicable in a variety of different situations and for a variety of different use cases. Now, what is a bandpass filter? I want you to imagine a tomato processing facility in which tomatoes excavated from the ground are cleaned and their stems are removed so that only the tomato is left behind. The bandpass filter operates similarly to the tomato processing facility in our analogy. It is a device that allows frequencies within a specific frequency range and attenuates frequencies outside that range to reach the desired result of a range of frequencies that one could want in a chosen application. In its most basic form, it's a cascade connection between a high-pass filter and a low-pass filter. This means that it has two cutoff frequencies, which make it useful in only accepting a specific range of frequencies. The higher cutoff frequency is decided by the high-pass filter, and the lower cutoff frequency is decided by the low-pass filter. Now, bandpass filters have many applications. They have been used frequently in LiDAR and laser technologies. They aid intricate measurements and are useful in the application of acquiring data. Bandpass filters are also used in audio signal processing for pinpointing the needed sound frequencies for the enhancement of audio fidelity. They are even used for the detection of seismic waves, which allow us to gain insights into earthquakes and undertake geological analysis. As part of our design, we will be using a Chebyshev bandpass filter, which is characterized by its steeper roll-off and is used for the applications that require specific frequency selection, like signal processing in radio frequency applications, filtering out unwanted signals and noise. So who was Chebyshev? Well, Chebyshev was a 19th century mathematician whose work on minimizing maximum error led to Chebyshev polynomials. These polynomials form the mathematical basis of Chebyshev filters. Now, why should we use a Chebyshev bandpass filter exactly? Why not use a Butterworth filter? Well, Chebyshev filters trade the small bandpass ripple for a much steeper roll-off compared to Butterworth filters of the same order. A 3-pole Chebyshev bandpass filter gives us that sharp attenuation outside the passband that we need and good frequency selectivity with only a small number of components. We use that controlled ripple to achieve sharper band edges, which makes it perfect, which makes it ideal for this bandpass application. Our project's aim is simple. We will design a 3-pole Chebyshev bandpass filter, which is a derivation of a normalized low-pass prototype filter. Included in this design will be a J-inverter circuit with inductor-only networks. This will be simulated and represented by a frequency decibel graph, displaying our desired frequency range. The design will also include a microstrip half-wavelength implementation. We will then graphically compare the electromagnetic simulation result with the J-inverter circuit model simulation result. As mentioned previously, a bandpass filter attenuates everything outside its frequency range. Ours is, by nature, the same. Listed here are our circuit design specifications. By necessity, our 3-pole Chebyshev bandpass filter must have a center frequency. The center frequency that we have been tasked with is a frequency of 1.6 GHz. To meet our project brief standards, we must also have a fractional bandwidth of 0.1 and a characteristic impedance of 50 ohms. As can be seen here, for our microstrip design, we will use a half-wavelength resonator with Rogers RT Duroid 6010 LM substrate. Our dielectric constant will equal 10.7, the microstrip thickness will be 1.27 millimeters, the loss tangent will equal 0.0023, and this will all be arrayed with a top and bottom copper cladding measured to be approximately 35 micrometers. We are given a normalized 3-pole low-pass prototype filter in the top left with its values so that we can derive our 3-pole Chebyshev bandpass filter from it. We'll use a scientific calculator, a pen, and a notepad to calculate the capacitance and inductance values for the normalized low-pass prototype filter. After doing this, we will simulate the circuit in ADS to get a graphical indication of whether the filter achieves our desired specifications. However, our circuit is not yet finished. As mentioned previously, our circuit design will be a J-inverter circuit, featuring inductor-only networks. We will use the prototype filter to derive the values for this new J-inverter circuit and calculate accordingly. When simulating, we should get a result with our desired center frequency. If it's not in that range, we can tune it so that we get to that desired frequency, or as close to it as remotely possible. Our microstrip layout consists of a half-wavelength resonator implementation. Now, before simulating our microstrip design in ADS, we must first calculate its values. This includes the gain and the substrate thickness. We'll use the equations given to us, and we'll calculate the theoretical coupling and practical coupling using the values as can be seen in our design specifications. We will also calculate our theoretical external quality factor and our practical external quality factor. These represent the coupling of an accelerating cavity to a power source. Therefore, they are very important in the use of our electromagnetic layout implementation. We'll design all this in ADS and use the equations listed to achieve our desired electromagnetic simulation result. This should display our center frequency. We'll then graphically compare our results from our circuit layout and our electromagnetic layout using either ADS or MATLAB. This project, according to our Gantt chart, should roughly take about 80 days. There is an initial stage of compiling calculations before any simulation is done in ADS. This is done both before the circuit layout and before the microstrip layout is simulated in ADS. It's very important that we always take time out for the theory and calculations of both our layouts before any simulation is done. We'll finally analyze our data, making final checks before beginning our design fabrication. All analysis of our data is done using a graph, is represented graphically, and our design fabrication should take roughly 11 days in the best case scenario. Note that this is only a guide about how long our project should take, and we'll do so to the best of our ability. Listed here are the many helpful sources of information we used. Included, of course, is Dr. Augustine, whose YouTube channel and paper on the circuit modeling of the bandpass channel filter proved both insightful and very helpful. Electric4u.com and the YIC Electronics blog were both incredibly useful in laying out the theory behind this important project. My name is Patrick Ngala, and I would like to thank you for your attention regarding our design proposal. Have a good day.